the first question is.
Oh, yes.
Yes.
There is a question.
Yes.
Can we go back to the certain node in the script?
Well, in principle, yes.
But in practice?
Yes, in practice.
Practice as well, yes.
Thank you.
So the first question is, which attribute to select as the root? For example, in the case I presented before, we can use as the root several different attributes like outlook, or temperature, or variety, or humidity. And which, how to decide which attribute, which feature to select as the root? Well, the idea of the standard idea of all these heuristics is so-called the idea to maximize purity. Let's assume that the initial data set, so there are several classes, the class of green points, orange points, and red points. And what we do in the node. In the node, you have some predicate, you have some decision which, in a binary way, divides the whole training data set into two parts. And so, to make this division, we try to organize this predicate in such a way that the resulting subsets from the initial data set, they are as pure as possible. I guess in case of classification, it's quite obvious what do I mean by saying pure. It means that the overall proportions of different classes in this subset should be as small as possible. I mean that I would prefer to have like all orange dots here and say all red dots here, or maybe all red and green dots here. And so the question is how to measure this thing so that we can optimize the corresponding criterion to automatically construct a predicate. What is a good attribute? We want to grow a simple tree, and a good attribute split the data so that each successor node is as pure as possible. For example, it contains mostly a single class. This is the idea. And we want to measure that prefers attributes with high degree of order. And maximum order means all examples of the same class, and minimum order means all classes are equally likely. And here is the standard measure how we define purity. So in case of binary classification, we can define purity in a very simple way using entropy. Let S be a set of examples. Let P plus be the proportional examples in positive class, and let P minus be the proportional examples in negative class. So the entropy, the formula to create the entropy for this binary case is like this, and the entropy attains its maximum in case this proportion P plus is equal to P minus and is equal to 1/2. But 1/2 means that in both subsets, it means that in the considered data set, you have half of positive examples and half of negative examples. So this is maximum, this is minimum order in some sense. In case you have not two classes but k classes, in this case you will create the entropy this way. So what we do next? First we should select which attribute, which feature to use as the root. What if we select the outlook as the root? In this case, when the outlook is sunny, we get 3 examples with yes and 2 examples with no. Oops, I'm sorry. Just a second. we have two examples with no and three examples with yes. So the entropy of this subset of data is equal to this value. Then, when the outlook is overcast, we have 4 examples with yes and 0 examples with no. Let me remind you the coefficient. So this is it. So we get here some training data set, and then if we select the attribute, the variable outlook as a root, then the outlook contains several values: sunny, overcast, or rainy. And so the whole data set will be divided into 3 subsets with such labels. And then we calculate entropy. So the entropy for the first subset is like this, the entropy for the second subset is like this, and the entropy for the third subset is like this. And so then we do the following. We take these entropies for the subsets and also weight this entropy with this weight which is proportional to the size of the subset. Because if the size of the subset is small, well, it's not so important actually. And so we then calculate the average entropy for the attribute outlook. It is equal to this, right? And so what we do next? We select such variable as the root variable. We select such feature for which this entropy is as small as possible. But the question is, how to compare what is small and what is big? Usually, in decision trees, they calculate so-called information gain. So let's assume that we have some set of data, and for that set of data, we can calculate the entropy of this set of data. Here is it. Then we take some variable with index number j, and with respect to this index number j, we calculate the average entropy if we divide the whole subset, the whole data set into subsets according to this variable, like we did with respect to the variable outlook. And we calculate this value, which is average entropy of dividing the initial data set into subsets according to the variable outlook. So we get this information gain. Here is it. This is the difference between two entropies. And the question, what we want to maximize the information gain. It means that when we select the variable with the highest information gain, it means that we divide the initial data set into subsets with maximum order, with very good pureness. And so we see that information gain for the variable outlook it is the biggest among other variables, and this is why we select the variable outlook as the root. So we do this, and we get 3 subsets. And what we observe that for this subset, when the outlook is overcast, all examples already have the label yes. So we don't need to do anything else in this case. But when the outlook is sunny or when the outlook is rain, in this case, this subset of data has some labels which is yes and some labels which are no. In this case, the situation is the same. And so, because of that, these subsets should be further splitted. Then what we do, we select the next variable with respect to which it is the most preferable to divide this subset which we get in this node. And we see that the gain for the humidity is the highest. And so we select the variable humidity. The variable humidity takes 2 values, high and normal. And when we do such split, we observe that the subsets we get, they are pure, because for the left subset of the initial data set, all labels are no, and here all labels are yes. That's it. So we get this part of the decision tree, and then we repeat the process for this node. Finally, we get this result. Any questions so far, guys?